Hello everyone, welcome to week 6 problem solving session. Today also we are going to solve graph problems. So I have already shared the problem link in the chat box to you. It is there on GitHub. And now let us look at the problem statements. These are very simple. Is there anything? Okay. So let's look at the problem statement is quite small, and I'll just read it out quickly. So the first problem is that determine the minimum cost to provide library access to all citizens of Wonderland. There are cities numbered from 1 to n. Currently there are no libraries and the cities are not connected. Bidirectional roads may be built between given city pairs listed in cities. A citizen has access to a library if their city contains a library, or they can travel by road from their city to a city containing a library. Okay, so it says that there are n cities numbered 1 to n, and currently they are not connected with each other, and there are no libraries in any city. Now we need to connect, we need to provide access to a library from all the cities. Now we can either construct a library in a city, or we can build roads between the cities so that people from another city can access the library in different city. So that's what it says. So a citizen has access to a library if there is a library in their city, or if they can travel by road from their city to a city containing a library. Okay, so for example, let's say this is the sample map of the Wonderland, where the dotted lines denote possible roads. So currently there are no roads, but you have been told that you can construct roads between the cities which are joined by these dotted lines. So you can construct a road only between city 1 and 7, because there is a dotted line there, but you cannot construct a road between 3 and 7. Okay, and you can construct a library in any city. Now you're also given, oh, I'm so sorry, I again forgot. I'm extremely sorry. Yeah, so I hope the screen is now visible. I forgot to share it. I'm reading the problem statement from here. So there are n cities 1 to n, and we have to provide library access to all the cities. Okay, and I was saying that a citizen has access to a library if there is a library in his or her city, or if they can travel by road from their city to a city containing a library. So like for example, if this is the map of the Wonderland, okay, then, and there are these cities 1 to 8, okay, denoted by the circles, and the dotted lines between the cities are actually the possible roads. So roads that you can construct, but currently there are no roads between the cities. Currently there is no library also. Now you have to tell like which roads can be constructed and where to construct the libraries so as to provide library access to all the citizens. Okay, and you will be given to a cost of road construction, which is same for all the roads. So let's call it CC road, which is the construction cost for the road. And you will also be given a cost to build a library, CLib. Okay, like for example, if for this given map, if CC road, cost of constructing the road is 2 and cost of constructing a library is 3, then if we build 5 roads, 1 2 3 4 5, then the cost will be 10, and libraries for a cost of 6. 1 2 3 and 1. Okay, so here we are saying that if we build, let's say, roads 1 2 2 3 and 3 1, and one road 5 6, okay, and one road 1 7. So let's build all the roads in this side of the graph, which is 1 7 1 3 1 2 and 2 3, and this side will build only one road, which is 5 6. So if we construct these 5 roads, then the cost of building the roads is 10. And if we then construct two libraries, one library let's say in city 1, one library let's say in city 6, one second, I just forgot. Sorry, so 5 roads will be actually here, like I'll just draw this. I'm so go to the whiteboard. Three, 2, 5 6 8. Okay, so if you have understood the problem, then how can you solve the problem? So the problem is just that you have to construct libraries in certain cities, and then you can in those cities which are not, where there is no library, you can construct roads to connect those cities to other cities which have library. Is like, so far is it clear what the problem is asking? Like for example, if we construct a library in city 1 and construct a library in city 6, okay, then we only need to build these roads. That's like, we need to build only these many roads. So we will be building 5 roads, and cost of building one road, which is given as 2. So this already gives us, like, we have spent 10 units in building the road. Then cost of library is given, building a library is given as 3, and we need to build here 2 libraries. So that is 6. So total cost here is 16. Total cost to connect all cities to libraries is 16. Okay, and this is the minimum possible. Other way is, of course, you can construct one library in each city, right? Now what will be the cost for that? If you construct one library in every city, then do you need to construct any roads? You won't need to construct any roads, because if you construct a library in every city, then every city has access to its own library. No need to construct any roads. But if we do that here, then the total cost will be 8 libraries into cost of constructing each library is 3, which is 24, which is more than 16. So that is not optimal here. Another way is that, let's say we construct the library no, this is fine. What could be the other way? No, I mean, unoptimal solutions, there are many possible. Of course, you can add more libraries, or construct this road also, which was not needed. So those are unoptimal, but this is the optimal. Cost is 16. Is this clear? Do you have any questions? Anyone, did you understand the problem?
Yes, ma'am.
Okay. Others, could you tell me in the chat box or by unmuting yourself if you understood the problem or not? Okay.
Yes, ma'am.
Okay. So okay. Manas, did you understand or not? I think you said yes by unmuting yourself. Okay. And Vishwajit, did you said yes?
Yes, ma'am.
Okay. Okay, so everyone understood what the problem is. Good. So then, so you will be given Q queries or T test cases, and for every test case you will be given the number of cities, the number of roads, the cost of building library, the cost of building road, and then you will be given M lines, where M lines contain a pair of nodes, you can say UI and VI, where you can construct the road between UI and VI. For example, this is one of the sample inputs. Like, consider only this. This is there are 2 test cases here, or 2 queries, and so this is the first query. Here first integer is 3, means there are 3 cities. Then there are 3 roads that can be constructed. Cost of library is 2, cost of road is 1. Then cities 1 and 2 can be connected, city 3 and 1 can be connected, and city 2, 3 can be connected. Okay, so let's look at this example. So here you are given, so 3 cities, 3 roads, bidirectional roads, where all can be connected together, and the cost of library is 2, and cost of building a road is 1. So here if you build a library in say 1, then that cost is 2. Then you can build 2 roads, like you can build either 1 to 2, then 2 to 3. That will add 2 more units, 1 unit for 1 to 2, then 1 unit for 2 to 3. Another possibility is that you constructed the library in 1, so you can either construct road 1 to 1 3 and don't construct 2 3, because that will be repetitive, you don't need that. So here the solution is that you only need to construct 2 roads, okay, and 1 library, and that will be your giving you a total cost of 4. Now for the next. Is this example clear? So for the next one, let's try to do this on the whiteboard. Yeah. So it says that you are given 6 cities, 6 roads can be constructed, and here yeah, so 6 cities, 6 roads can be constructed, cost of library is 2, cost of road is 5, and these are the roads. So if we draw this, then it will be like 1 3 4 2 3 5 6. So it's like 1 3 can be 3 4 can be connected, 2 4 1 2, and then 5 6. So it's similar to the example that we have already seen. So could you work this out and tell? Here cost of library is 2, cost of road is 5. Are you guys working like trying to solve this? Can you share the problem link once again? Yeah, sure. Yeah, I've shared the problem link and answer is 24. Let's see. No. Answer is less than 24. But okay, 21. Okay, fine. 21, it's even less than 21, but can one of you tell me where will you put the library and which roads are you connecting to get 24 or 21?
For 21, make a pair of nodes.
Okay.
1 library and 1 road. 7 into 3. 3 nodes.
1 library.
As road cost is more, we will not make more roads.
Okay. So then?
We make pair of 1 3 5, 6 and 2, 4.
1, 3, 5, 6. So you are saying these roads have to be constructed 1, 3, 5, 6, right?
1 and 3, one road
Okay.
with library in 1.
Okay.
2 and 4,
Okay.
road, library in 2.
Okay.
5 and 6, road, library in 6.
Okay. Okay. And you're doing this because like constructing cost of library is less than that of road.
Yeah, if we want to connect. Otherwise, we can make library in every city.
Yeah, so do that. Right?
That will be 18 or
That will
no,
be 12.
12. Yeah.
Yes. Yeah, so that is the optimal answer. Because we are told that we only have to provide access to library to every city. Right? Either by building a library in their own city or by providing a road connection to other cities that have library. So here, since the cost of library is less than cost of road, then we can build a library in every city, and that will be the optimal answer. Now why it's optimal is because if there are n cities, okay, right, if there are n cities and you build, sorry, libraries I wanted to write, if there are n cities and you build a library in every city, so this will be the cost, total cost. Okay, but if there are n cities and you build a single library, so that will be like CLib, plus you build, how many roads will be required? If you build one single library at one city and there are n nodes, okay, and then how many roads, minimum roads need to be constructed so that every city has access to this library? I'm assuming that all of these cities are connected, can be connected.
N-1 roads.
Yeah. Like for example in this one, like 1, 3, 2, 4, here since there are only there are four nodes, we need to construct only 3 roads to connect them to each other. If we have constructed 3 roads, then we can traverse from any city to any other city. So n-1 into C road. So now it is quite clear that if C road is greater than C library, then this will always be smaller value. So therefore, whenever C road is greater than C library, the answer is n times C library. We construct a library in every city, right? Is it clear to others and everyone? Between 2, 3, 2, 3, was there? Okay, sorry. Yeah, it was there here. Thanks. Yeah, it's not being updated, so I've added it, but it's not getting update. It has not yet updated here. Okay, so is this clear why we will why will the answer be n times cost of library when the cost of library is less than cost of road? Okay, then when cost of library is not less than cost of road, what will you do? How will you solve the problem?
I guess number of connected components minus
Yeah.
times cost of road.
Yeah, say again.
Number of connected components minus 1 times cost of road plus the library needed in each component into cost of library.
Okay, number of connected components are right here. We are saying number of connected components multiplied by cost of road, then
Number of connected components minus 1 times cost of road
minus 1 times cost of road
plus the library needed, like number of library needed to fill each connected component with like at least one library times cost of library.
So how will you write that then? That will be like number of connected components. That many libraries you'll need, right? Times cost of library.
Maybe less, like if a connected component has or has a library, then we don't need any additional library.
No. What's a connected component? So like this 1, 3, 2, 4. This is one connected component. And 2, 5, 5 and 6 is another connected component. Right? So we have here two connected components. Now there is no way to go from any node here in this side. Like there is no way to go from 1 to 5. So even if we have a library in 5, we can't use it from any city 1, 3, 2, 3, 4. So therefore we need one library in every connected component. Right?
Wait, I said something wrong, I guess.
Yeah, it's okay. But you are in right direction. So just yeah, so anybody else? Can anybody else try? Who was answering last time?
It was me.
Okay, okay. Yeah, you were correct about the number of the number of connected components is playing a role here. So it is like, just I'll give a hint and then I want you to think about it. Let's construct one library in every connected component because that is the minimum we need, right? And then we construct the minimum number of roads in that connected component. So if it's a connected component, that means we can reach from any city to any other city. So if here I construct a library in city 3, then I can reach here from 1 to 4, any city, right? So construct one library in every connected component, and then in one connected component you need to construct the minimum number of roads. What is minimum number of roads to connect n nodes?
N-1.
Yeah, so we need n minus 1 edges here, n minus 1 roads, right? So that's the answer. You just need to like now if you can try to tell me how will you solve.
So for the second condition, when cost of library is greater than cost of road, for each of the component we have to calculate separately. Or
Yeah. Yeah, so total cost is initially, let's say, 0. Then for each connected component we are going to add total costs plus is equal to cost of library. We'll build one library, and let's say the size of the connected component is s, then s minus 1 times cost of road. This we will do for every connected component, where s is size of connected component. That is the number of nodes in that connected component. Does this make sense? Like for example, if we go back to our previous example here, so this one here, there are two connected components. So first connected component, we will construct one library. So total cost is equal to 3 for for constructing one library, right? And then the first connected component has 4 nodes. So 4 minus 1, 3. 3 times cost of road is 2. Plus for the second connected component we have we construct one library. plus there are 3 nodes, so we construct 2 roads, and the cost of constructing 1 road is 2. So that gives us the answer. Right? Anybody? Is it clear or not? Is this clear?
Yes.
Okay. Others? If it is not clear, then let me know. Or you can type in the chat box saying yes, no. I can repeat if it's not clear. Okay, okay. So can any one of you volunteer to tell me how did we solve, what was the problem? Okay. Okay. Vishwajit, can you tell me the solution now?
Yeah.
Okay. Yeah, please go ahead.
So the cost of library is strictly less than the cost of road, and we can simply construct a library in each city.
Yeah.
Otherwise, we'll construct library in each connected component,
Yeah.
and uh, plus we'll join the cities in a particular connected component by the number of cities in that connected component minus 1 roads. We go on for the every connected component like that.
Yeah. Yeah. Yeah, I hope it is clear to everyone. So that's all, like that's the problem here, and this was the problem. So now let's go to quickly to second problem. So if you have any questions about first problem, then it's time that you tell me not to go to problem number 2, because then I can spend rest of the time in this session talking about problem number 1. But since you have no doubts, so let's go to problem number 2. So Jack has just moved to a new city called Rapture. He wants to use the public transport system, and the fare rule are as follows. Each pair of connected stations has a fare assigned to it regardless of direction of travel. So that just means that all the roads are bidirectional, okay? And if Jack travels from station A to station B, he only has to pay the difference, that the fare from A to B and the cumulative fare paid to reach station A. So which is fare A comma B minus total fare to reach station A. And if the difference is negative, then the travel is free of cost from A to B. So for example, I'll just explain this with an example here. Let's say Jack travels from 1 to 2 and it costed 20 units. Now to travel from 2 to 4, he only needs to pay 30 minus 20, which is 10. So he only needs to pay 10. So cost of reaching 4 from 1 for Jack will be 20 plus 10, which is 30. Okay, so that is here. If on the other hand, if it were, let's say, 10 here instead of 30, if the edge 2 to 4 were 10, then the cost from going from 1 to 2 would be 20. And then here the rule says that cost from 2 to 4 is fare of 2 to 4, which is 10, minus total fare to reach 2, which is 20. That becomes negative. 10 minus 20 is minus 10. So then Jack does not need to pay anything for the edge 2 to 4. And he can reach node 4 in only 20 units, which he paid for edge 1 to 2. Okay, so that's what it's saying here. Now Jack is low on cash and needs your help to figure out the most cost efficient way to go from first station to the last station. Given the number of stations, G nodes, and the fares weights between the edges between the G edge pair of stations that are connected, determine the lowest fare from station 1 to station G nodes. So here, so G nodes, you can just say, simply say there are n nodes, there are m edges, and you are asked what is the minimum cost to reach from station 1 to station n, that you have to reply. So read the problem while I draw the example, and then we'll look at the example. Okay, any questions with the problem statement? Send the link. So it is in the same PDF. It starts from the next page, page 4. Okay, and now coming back here, I hope the question is clear. So if for this example graph, we need to go from 1 to 4. Okay, so if we travel from station 1, then 2, then 4, so it costs 20 for the first segment, which is 1 to 2, right? And then cost the differential, which is 30 minus 20, 10. So the total cost is 30. And then if we take the another road, which is 1, 3 and 4, so the first edge here costs us 5 unit, and then for the next edge 3 to 4, we will have additional cost of 40 minus 5, which is 35. So total cost becomes 5 plus 35, 40. And the lower priced option is to take 1, 2, 4 with cost 30. Now you have to output the lowest possible cost of the path you can take from 1 to 4, 1 to n, not 4, 1 to n. And if no such path exists, then you need to print no path exists. And the input format will be, you will be given nm, like number of nodes, number of edges, and then you will be given UVW, where U is the start, no, U is where there is a edge between U and V with the weight W. So that is like the standard input format which will be given to you. So, like for example, if this is the graph that you are given, then tell me, can you just try this on pen and paper, then find out what will be the answer, what will be the lowest cost to reach from node 1 to 5.
That will be 30
Path 2.
of part 2. Yes.
30, no, so I think we misunderstood the problem a little bit here. So we have to
Only
keep
130.
adding. So like in this example, if we take the path 1 to 4, then the first segment costed us 20, okay, and second segment costed 10, which was the differential. 30 minus whatever the cost of reaching the previous node was, which was 2, and the cost was 20, but we take the addition of them. So 20 plus 10 gives us 30. Right? So the first segment 1 to 2 costed 20, and the second segment fare was reduced actually from 30 to only 10. And this is the rule by which it reduces. If the difference between fare A comma B and total fare to reach station A is positive, then that will be the new fare. If the difference is negative, then there will be no cost. It becomes 0.
Cost 90, path 1.
90. Okay, how is it 90?
130.
Till node 2 we have 60.
Yeah.
We reach node 3.
Yeah.
The difference is 20. 20 plus the previous path 60.
Yeah.
That is 80.
Yeah.
We
here
go to node 5.
Hmm.
That is 70 minus 80.
Yeah.
10. 10 plus the previous
No, it's
total
minus
cost
10.
is
Madam, sorry, it's 80, not 90.
Yeah, because it's minus 10, right? 70 minus 80 is minus 10. Here the rule is that the new fare is fare of A comma B minus the total fare to reach station A. And if the difference is negative, then travel is free of cost from A to B. So for this example, 70 minus 80 is minus 10, which is negative. So this edge you can travel free of cost.
Madam,
Yeah.
uh, instead of starting from 1, if we start from n, that means our goal node to the starting node, and we will consider every edge that contain less less cost, then will it work?
Every edge that contains less cost. Like for example, in this.
For example, 5, instead of starting from 1, we start from 5, and from here we have two edges, 70 and 50 cost. So we will
150.
choose 70.
Okay. Yeah, but you can do the same from 1 also. I mean, it's same. It does not matter. It's a undirected graph.
Yes, ma'am. Yes, ma'am.
So, is is this clear why the answer is 80 and not 90? Because this fare is negative and therefore we do not add this. It the cost of this edge becomes 0 and this is the cost of fare. So, I'll just so if we work this out, so it's like 1 to 2 cost was 60, then here we have 80 minus 60 plus addition of 20, so cost here becomes 80, and here 80 plus 0, because 70 minus 80 is equal to minus 10, which is negative, so it becomes 80. If we took the other path 2, then it would be 120 here, and then it becomes 120 plus 150 minus 120, which is 150, so 150, and the optimal one is 80.
Madam,
Yeah.
madam, in the previous, that means our in the question, the graph that is given, if we start from the first node and we choose lowest cost node, then we'll go from 1, 3, and 4. So therefore, we'll get means maximum one. Sorry, not maximum, but we will not get a minimum one.
Yeah.
Therefore, I thought we will start from a goal node.
Yeah, that will not work. But the cost function is clear, right?
Yes, ma'am.
It does not keep adding. There is a different cost function here. And we can simplify the cost function here. So it is like when you're going from A to B. So now cost, I'll write here. So if you're going from A to B, then if fare A comma B is greater than cost of A, 1 to A, that is the cost, the amount you've spent to reach from 1 to A, then cost 1 comma B will be nothing but fare of B, sorry, A comma B. So here, okay, it's not visible. So I'm saying if the fare of the h a comma b is greater than cost of reaching node A, then the cost from going from 1 to B is equal to the fare A comma B. Because what we are doing is that we are adding to cost 1 comma A, so we change it, so it's just that cost 1 comma B is equal to cost 1 comma A plus fare A comma B minus cost 1 comma A, right? And these two cancel out. So that's what I'm just saying. So if it is positive, if fare A comma B is greater than cost 1 comma A, then cost 1 comma B is just equal to fare A comma B. And if it were negative, then this value in the bracket would have been considered 0, and therefore the cost 1 comma B becomes equal to cost 1 comma A. And that's just something that I wanted to mention in terms of the cost function here.
It's the maximum of 2, right?
Yeah. Yeah, right. It's the maximum of the two. Yeah, it's the maximum of the two. So just as a hint, you have already studied the algorithm that you can apply here in week 6. Only the cost function is here a little difference, but it is still monotonic. It's if you take a longer path than the earlier one, like you have 1 to A, you went from 1 to A, then you take other edge A to B, then your cost might not increase. It can remain same, but it will never decrease. So it's still a monotonic, the increasing cost function, weakly monotonic, not strictly.
I guess it's the part whose maximum edge is the smallest and maximum edge weight.
Maximum edge weight is the smallest. You're saying 80, like that.
Yeah, like if we consider 1, 2, 3, 4, then the maximum edge weight is 80, and if we consider 1, 4, 5, then the maximum edge weight is 150, and the smallest of the two is 80. So we will consider 1, 2, 3, 5.
Okay. So basically you will have you'll find all the paths from 1 to 5, right? And in those paths you are saying where the maximum cost, maximum edge weight is the smallest, you pick that. Yeah. Because the cost cannot go more than the maximum edge.
Madam, I
Right.
think it's right.
Yeah, I mean, that is right. So then, how will you solve? I mean, how will you uh, enumerate all of these paths? Because I think you need to look all the paths, right? So how many paths are possible, and so here actually it is like the graph is such that, but since it's a connected undirected graph, so then do we have any bound over the number of paths? Or is the number of paths, let's say we take only simple paths, we will not repeat
The number of
edges.
paths won't go beyond n into n minus 1 by 2.
N into n minus 1 by 2 is the number of edges. A simple path is of length n minus 1. Yeah, I think that will work, but why is the bound over the number of paths n into n minus 1 by 2? So there are n into n minus 1 by 2 edges, right? To construct one path. I don't know if you can arbitrarily pick edges, but if there are say n square edges and you have to pick any n minus 1 edges, because one simple path will have n minus 1 edges, so you can pick like n square c1 times n square minus 1, so it's like n square times n square minus 1 times n square minus 2 dot dot n square minus n plus 1. Am I wrong? Like, why is n into n minus 1 by 2? Number of simple parts. Yeah, so I just quickly searched and found that the time complexity, so every permutation of the vertices will give us one path. Yeah, that makes sense. So since it's a connected complete graph, like worst case we can have a connected graph where every vertex is connected to every other vertex. So then to reach from 1 to n, we need only like every permutation that we can construct from by fixing 1 and n, all the other vertices we can just permute them. So that is n minus 2 factorial. So order of n factorial, right? N into n minus 1 times n minus 2 times. So that many paths will be there, n factorial.
And that will be lot, I guess. Then the Dijkstra will also work here.
Yeah, so the first approach that you suggested, while it's correct, but the time complexity is huge because there are a lot of paths possible, order of n factorial. So yeah, Dijkstra here works, and Dijkstra we can use here, which is the shortest path algorithm, right? So we will give us the shortest path to reach from 1 to n. And all we need to do is just change the cost function, and as you rightly pointed out, that is like the cost will be the max here. So when we are updating the cost of the finding how to update, so earlier we would just take the cost to reach say intermediate node plus the cost of the edge. Now the cost is actually the maximum of the cost to reach the intermediate node and comma the cost of the edge. So that is the update. Now you check whether the update is less than the current cost of the node or not. If it is less, then you update, otherwise don't update.
Madam, can you repeat?
Yeah. Okay. Yeah, just let me connect to my whiteboard. So I am saying here that in Dijkstra, when we pick the next node, so in Dijkstra we will pick a node which is having the shortest distance so far, like current shortest distance, right? That we do. So at that step, we are going to relax all the edges which have not been relaxed yet, which are all the edges outgoing from it which have not been relaxed yet. So then by relaxation, what we do, we update their cost. So I'm saying, how do we update the cost now? That's just a very simple difference is there from Dijkstra that we have studied or applied before, and that is that earlier update cost which you would find would be something like d of v. If v is the current cost plus if so let me just not call, if u is the current cost, and so whatever is the distance that u has currently plus the edge weight, so edge weight w u comma v. So you want to relax the edge u comma v. So that was the update cost, and then you would check if distance of v is less than the update is greater. If it is greater than the update cost, then you would update distance of v. Here the only difference is that update cost is equal to max of dv comma this h w u comma v. Sorry, du, it's u. Yeah. Sorry about the whiteboard. And this is same. Is this clear? So we can solve the second problem using Dijkstra, and only we need to just change this update function, update value that we use. From doing addition of the distance to u plus the edge weight, we just take the max of distance to the intermediate node u and the length of the next edge. Yeah, so any questions here? Okay, so I had only these two questions to discuss today, and both of these questions are on HackerRank, and I will be posting the link to both of the questions in the PDF. You can go and try these questions on HackerRank. Okay. Do you have any questions?
No, ma'am.
Okay. Thanks for joining.
Thank you, ma'am.
Thank you.